Welcome back to Engineering Data Analysis. We are now in lecture 4, or starting the main topic of probability. The last lecture was all about data. What is it, how to collect it, and the collected data forming our variables. In this lecture and the next two, we will be talking about the next part of our data. See, in the course of a study, the data collected would lend a certain pattern or behavior. We are after that behavior or pattern, the correlation or causation we have talked about previously, and this is where probability comes in. Probability is the likelihood of a certain event occurring. Well, in the course of the discussion and in life in general, we will always encounter flukes or outliers, and those are beyond studies or researches because we would like to know those that fall within majority, going with the flow. This is where the probability distribution will come in later and in the next main topic, but I'm getting ahead. So let me say that this lecture should introduce you to the concepts behind probability. The next two should tackle the counting rules and the rules of probability. The two lectures on rules should enable the students in correctly determining the probability of events. Let us start with definitions. We begin with the concept of a random experiment, and it is a mechanism or an activity with a definite outcome that we have no idea of what will result to. All possible outcomes of the random experiment are said to belong to a set called the sample space. Every outcome that is in the sample space is an event that can be observed with the random experiment every time it is carried out. Consider now a coin tossing experiment. By definition, it is a random experiment. Why? Because when you toss a coin, you don't know what face will fall, on what face will be facing you. Okay. Tossing the coin will result either with a head or on the obverse coin side, or a tail in the reverse. Head and tail are the events that can be observed in tossing a coin. Again, there is a fluke or outlier in this kind of event, as you may think, and that would be if the coin fell on its edge. You will have to neglect that outcome for the sake of simplicity. Thus, the set of events of the head and tail is the set of the sample space S. Okay. What about now the rolling of a die? This is a six-sided die. There are other dies that are of different sides. If you spread out the six sides, okay, and see the markings, we will be able to see that it has the same sample space as the set containing the discrete numbers 1, 2, 3, 4, 5, and 6. Now, let's go to sample activities around the use of the die. Suppose it is needed to determine or find the events corresponding to when an event has an even number Okay, what is the uh, sample space? Okay, yeah, or what is the events in the sample space that are even? Okay, even number. So you have already identified the sample space. What is there to do is just identify from the sample space the events satisfying the condition of the event, which is to be an even number. So the answer is, okay, those numbers are 2, 4, and 6. Next, if it is now the events that correspond to when a number is greater than 2 is rolled, okay? This will result to the number of events, okay? What is greater than 2, 3, 4, 5, and 6? Okay, last example is the set of events with a number less than 1, and this will result to what? This is called, in mathematics, an empty set. Okay, let's have an example denoting E as an event in the sample space S that has the chance of occurrence with a random experiment. Let us also denote the probability of an event as P of E. So mathematically, the probability of P of E is the number of elements of E divided by the number of elements of S, or in equation form, N of E over N of S. Now, we have a question here, okay? Find the probability of events that correspond to when an even number is rolled. We're now talking about the probability. Let us return to the examples from a while ago where we identified the events in E in die rolling to get the probability of the events corresponding to even numbers. Okay, the task is to simply count the elements of E, or the even numbers or even number events, and divide this by the total number of elements in the sample space. And this will become what? We have the elements 2, 4, 6 over the elements, okay, we have 6 elements in the sample space. That will be N over E divided by N over N of S. Okay, that would be 3 elements in N of E, and the elements of S numbering 6. That would result to a probability of 1/2. This means that when you draw, okay, when you roll a die, the probability of you getting a 2, a 4, or a 6 is 1/2. Okay, now next is same example. Find the probability of events that correspond to when a number greater than 2 is rolled. Okay, when will the 2 occur? Counting the elements of E, or the numbers greater than 2. And okay, what are these events? We have 3, 4, 5, 6. And the total number of the elements in the sample space, we have, okay, 4 over 6, which is 2/3. So the probability of drawing, or not really drawing, of rolling a 3, a 4, or a 5, or a 6 is 2/3. The last one, we will have the sample space, the empty set example. Since counting the elements of E in this case will always result with no elements or 0, we have 0 over 6, and we'll have give us the probability of 0. So there's no chance that this will ever occur. We have to expand the definition of probability based on the examples. Recall that the probability of an event E is the number of the elements or outcomes of the event E divided by uh, the number of the elements of the sample space. The probability of an event E in the sample space S occurring in a single, take note, single trial of a random experiment can take any value between 0 and 1, where 0 indicates an impossible event and 1 being certain. Okay? Please take note of this definition. Also, the individual probabilities of the different outcomes sum up to the probability of the event. Okay? Okay, we have here the individual events, E1, E2, up to EI, representing the individual events, okay, their probabilities, they will all add up to 1, okay. What we want to show here is that, for example, since there are 6 elements in the sample space, rolling a die will give you each element or each number will have an equal chance, well, regardless of the design of the dice. But we want to make sure that this die is perfectly cubic. Okay, so well, it could there's a possibility that the shape of the die can affect the outcome. But we're not talking here about the physical realm, but the mathematical realm, okay? So each element in the sample space has an equal chance of occurring or being rolled out. Okay, let's go back to another, well, this now we find the probability of events that correspond to when an even number is rolled, okay? Let us illustrate this with the first example from the probability of events that correspond to when an even number is rolled. Okay, we have the individual probabilities of the individual outcomes 2, okay, 4, and 6. We use the definition of P of E to give us the equation where we have the sum of these different probabilities. So substituting, we have 1 over 6 plus 1 over 6 plus 1 over 6. Okay? Adding the fractions with a common denominator, we get the answer 3 over 6. And simplifying the fraction, we have 1 half, or in decimal, 0.5. This is now as defined. 0.5 is between 0 and 1. This also means that there is a 50% chance of getting an even number in a single die rolling activity. This has the same probability of landing a head or tail in a coin toss. Okay? We'll now go to the sample space and, well, the event relations of sample spaces. I know, sorry, the relationships of events. Because there can be multiple events in a single sample space, and these events can be related to each other. So the first event that we're going to tackle is the complementary event. The complementary set, EK, is the set of all outcomes in the sample space not in event E. So shown is a representative Venn diagram. Another event relation is mutual exclusivity. We have been talking about this in the topic variables. And this refers to events having no common elements between each other. This also means that these events can happen simultaneously. This therefore excludes events in steps or successions that have no replacements. Okay, we will discuss that later. Succession will be detailed also. Another event are independent events. Two events E1 and E2 are independent if E1 does not in any way affect the occurrence of E2. This is not this easily represented in a Venn diagram, but just to show you that E1 and E2 in this diagram can be independent, given that they have common elements between them. This event relation is best represented with an illustration of two events of drawing cards from well-shuffled card deck. Okay, a card deck has 52 cards. Here, the event of drawing a king, there are four in a card deck. Okay, diamond, the spade, okay, the heart, and the okay. So the drawing of a king is independent with the event of drawing a diamond card. So we have two events, and these are independent events. Last, we have the combined events of union and intersection. With union, the outcome is everything in the two events. The conditions are further elaborated elaborated on by the statements 1, 2, 3. Okay, but basically just the same. It's all of the events E1 and E2, and you have the example there shown. Okay, all of E1 and all of E2, that is the union. Conversely, intersection consists the elements or outcomes in both events. So you have the intersection, the inverse U. U is representative of a union. The inverse U is intersection. So in comparison to union, intersection merely is statement number 3, or the outcomes of E1 and E2 joined together. Okay. So what is common between the two? All right, in the next lecture, we'll be talking about the rules used, or the counting rules used in probability, and much later, the rules of probability. I will see you then.